So just a few words about Christodoulou. He is a senior executive and the chief engineer at Transport for New South Wales in Australia, with accountability for all technical standards and specifications across rail, roads, maritime, and buses. He is a technical expert in bridge management with a specialization on corrosion asset management, durability, design, and electrochemical treatments. Christian's work spans across the United States of America, UK, Middle East, Australia, and New Zealand. So now I ask Eduardo to please put on the video.
Good day, everyone, and a very warm welcome to this FIB Bulletin 102 webinar on protection and repair of concrete structures. My name is Christodoulou, and I will likely be your presenter for today. Unfortunately, because of the time difference and the fact that I'm actually located on the other side of the world, in particular in Australia, I won't be able to actually join you live today for this event. So you are actually having a pre-recording of this session. As I said, I am actually based in Australia, so as it's customary here, I would like to start with a short acknowledgement of country, and I would like to acknowledge the Baromatangkal people of the Darug Nation and pay my respects to the traditional custodians of the land on which we meet wherever we are here today, especially elders past and present, and I acknowledge other Aboriginal people that may have actually joined us here. Thank you. Today, I would like to be talking to you about silanes and siloxanes, but most importantly, I would like to actually start with durability. Durability of concrete structures is of utmost importance, and without a doubt, a subject that we actually is occupying a lot of our time nowadays. As you can see from this particular slide, the design life of structures really varies depending on the intent they've actually been designed for. So temporary structures may only need to last for about 10 years, but when we likely start looking at buildings and other common structures that goes into 50 years, but also then when we're looking to the likes of bridges, major civil engineering structures such as tunnels or monuments, we're actually now moving into the 120 years plus. But fundamentally, when we're looking into durability, we actually want to ensure that we can actually meet the requirements of serviceability that typically relate around the loading, the cracking, the deflections, but also those of strength and stability through the design working life without significant loss of utility or excessive unforeseen maintenance. And I think it's that latter part that is actually causing us a lot of issues nowadays. We all accept that we'll actually have to apply routine operation and maintenance, but when you have to actually intervene to actually apply major repair or rehabilitation of your structure, is not actually meeting that intended serviceability and durability requirement. Now, I do actually remember my early days, even when I was actually a student. Most people actually think of concrete as a material that is gray or brownish in color-ish, and one that is actually consistent. In reality, concrete is naturally porous and it is inhomogeneous. And you can really actually get the appreciation of that when you actually slice through it and you put it under the microscope. It's very important to also remember that the size and distribution of all the pores in the concrete varies from one to another, and it really actually depends on the mixture of the constituent materials, the quality of compaction, the different materials that are actually used in the mixed design and the location that one may be, the water to cement ratio, which will actually affect its hydration, and of course the curing that will actually be applied. But fundamentally, concrete is not a proprietary product, it's non-proprietary. What that means is, while we can actually go and source concrete from different manufacturers, it's not a standardized product off the shelf in the same way that you'll actually go and buy a replacement light bulb for your living room. Also, the service life of concrete structures tends to actually vary. Now, in the past, we actually had a very simple approach of deemed to satisfy. So if the designer and the contractor met X, then its durability in theory should have actually been satisfied. So, and these are actually still inscribed quite significantly across a lot of specifications and standards today that tend to actually be prescriptive and follow that deemed to satisfy approach. But in reality, we all actually slowly moving towards an approach where we want to actually have a greater level of intelligence, monitoring and proving the service life. Of course, if you're now looking into assets such as tunnels, bridges and others with 120 years design life, you need to actually look at the whole of life cycle, understand how often you may need to actually intervene in order to achieve that intended service life, and how that actually fits with your concept of operations and maintenance. And I think that latter, speaking also now working for an asset owner, it's actually very important. It's one thing to actually design, construct and hand over a tunnel or a bridge, and it's a completely different matter to ensure that you continue to actually operate and maintain it in accordance to the service KPIs for your customers. Before we go into too much detail around hydrophobic impregnations, I really want to discuss briefly the transport mechanisms for the ingress of water, gases and ions. So fundamentally, these are threefold. You've actually got diffusion of free molecules or ions, which will actually happen due to a concentration difference. You can actually have permeation of gases or liquids through water-saturated specimens due to hydraulic pressure difference, or capillary suction of liquids due to surface tension acting in capillaries. So typically, the majority of this will actually happen either due to diffusion or capillary action. Permeation, unless you are actually under an environment where you've actually got full water saturation and you are immersed underwater to actually have that hydraulic pressure, in the majority of cases, it doesn't actually happen. Capillary will actually tend to be the first one transport mechanism that will actually kick in place, because that's where you'll actually have that contact between your concrete surface and a liquid. And in the long term, diffusion will actually add to that effect, because there will actually be always that concentration difference from the outer edge or your outer fiber of the exposure phase to the other side, or perhaps to your core, which may be at nil, and that concentration difference will actually continue to actually drive diffusion pretty much in perpetuity. Now that we actually understand the protection mechanisms, people actually tend to actually apply three different surface protection approaches. The first one includes surface coatings. They're very common, such as waterproofings or others. The second one is that of pore blockers. So there will be specific constituents that you may want to actually apply at the surface of your concrete in order to actually block those pores and therefore reduce that capillary absorption. And the third one are pore liners. Today, since we're actually talking around silanes, I will actually focus on that third form of pore liner. Now, fundamentally, silanes belong to a group of silicons, which actually contains just one atom of silicon. A typical example, and this is of an alkyl alkoxysilane, is actually illustrated in that chemical composition that you can actually see on your screen. You'll actually got your silicate atom at the center, and then you'll also have your alkoxy groups, which will actually be linked to the silicate via oxygen bonds. So typically you have three or more. So, and in addition to that, you'll actually have what we call the organic alkylic group. This is actually the group that remains, and that's the one that will actually protrude through the structure of the silane, and it will actually provide that hydrophobic behavior on your concrete. Fundamentally, if you can actually think about it and you can actually make it analogous to soap, it's actually the organic alkylic group provide that fatty character that will actually help you to actually line up the pore wall, and it will actually result into the formation of the hydrophobic layer. Now, having a silane application and through that hydrophobic surface layer, it will likely suppress the ingress of liquid water and any other corrosive agents which may be carried by water. Now, it's important to remember that while on the other hand, you'll actually have that lining, silanes do not actually block the concrete micropores. And in fact, it will allow water vapor to pass unhindered through the concrete pores and to evaporate from the treated concrete surface. So this is, if you like, allows the concrete to breathe and actually dry out. Silanes typically have actually been associated with a low cost of application and also with a very low maintenance cost through the life. They can be pretty easy to actually apply, and it's something that we'll actually cover a bit later in today's presentation onto the application forms. But because of the chemical composition, they have typically got a bad reputation because they can actually be harmful both to the environment, but also to the labor that will actually install and apply them in the first instance. So some countries or some actually transport agencies is discouraging the use for that particular reason, especially if you are in an environmentally sensitive area or if you're actually walking close to water courses. But fundamentally, the surface impregnation of reinforced concrete structures is very useful because it can really help to prevent the ingress of water and dissolved deleterious substances such as chlorides. Now, a structure that is protected against water and subsequently chloride ingress can actually attain a longer life with a reduced maintenance regime. Therefore, this protection or repair method can actually be really effective in protecting the concrete from chloride attack. In particular, surface impregnation is very well suited to surface areas which are not subjected to traffic, and as a subsequent, there is no mechanical wear of that impregnated surface. In other words, there wouldn't actually be a pumping transfer of the deleterious materials into the substrate due to contact with the running surface. It can also be used into brand new structures, not just actually into existing and aging infrastructure. And when you actually apply a hydrophobic treatment at that early stage, it can actually be regarded as an additional measure to protect young concrete and help it to achieve that surface life. But equally, it's important to actually understand when you applied what is actually the current condition of the concrete, and it's something that we'll actually unpack a little bit more detail in the next few slides. So before you actually think that this is actually the solution for everything and anything, and you actually embark and start applying silanes and siloxanes across all your assets, is it really important to actually consider the following. First and foremost, what is actually the current structural condition of our assets? If our asset is actually in a very benign environment or actually very young in age and is not actually affected by significant chloride contamination, then definitely silane can actually be of help. However, if we can already see that we've actually got significant chloride contamination and potentially has actually reached that reinforcement level, and even worse, it has actually reached that critical threshold level, then silane will not do a lot, and it will not actually stop the corrosion process and also the destabilization of that passive layer on the reinforcement. So it's very important to really understand that. Of course, we also need to actually take into account what are the budget constraints that the asset owner may actually have. So money is actually finite, so make it actually go a long way is very important. Last but not least, one has to actually take into account what is the outcome that we want to actually achieve? Do we want to actually give a new lease of life to existing structures which have not actually suffered significant contamination? Do we want to actually simply slow down the corrosion rate temporarily by allowing the concrete to dry out and actually stopping new chlorides coming through? Or is it actually something that we want to apply into young concrete in order to actually give it an extra layer of protection? All of these actually should come together, and of course they should be commensurate with the service life extension that we want to achieve. In terms of design, we touched upon structural condition, and that is actually very important. Don't be surprised if your asset is already suffering from significant chloride contamination, and then you actually attempt to apply a silane treatment, and then you see deterioration of the concrete happening a few years later or at some point down the line. That's not to say that your silane treatment has not actually worked effectively, but it suggests that the contamination was already too significant and all you actually managed to achieve was a bit of a slowdown. Exposure to UV can actually be a bit detrimental into the long-term performance of the silanes and also rain. Now, especially the latter may sound a bit of an oxymoron because it's actually supposed to reduce the water absorption, but what this actually means is it's actually, as part of the normal wear, it may actually reduce its effectiveness a little bit quicker than if it was actually sheltered. You also need to actually consider the variety of products that exist out on the market, the surface preparation that will be required. This is linked back into the porosity of your structure, the moisture content, and the dosage that you may want to actually apply. In terms of application, it's actually pretty straightforward. Every manufacturer they will have their own recommendations in terms of what you can actually do, but the most common methods of application will be either by brush or by spraying, and the latter can be by low pressure spray or early spray, where you may actually ionize the atoms into the silicate atoms into the solution in order to actually get the achievement. So pretty straightforward, and as I said earlier, each and every manufacturer will have their recommendations with respect to that. Quality control is very important, so understanding the ambient weather conditions and that to be recorded is actually an important step of the application. Understanding the moisture of the substrate and the dew point, and of course understanding what will actually be the required application rate of the material, the dosage as we actually typically call it. All of these are actually factors that can actually affect the long-term performance of the silane treatment, and it may actually get it to last longer or shorter. It may also affect its penetration depth, and its penetration depth has actually been shown through studies to be very closely linked into that protective layer and also the long-term performance. In terms of long-term monitoring, in reality, none is actually required. So the majority of those products are actually being sold as apply and forget, but it is actually advisable for every now and then to actually check for the efficacy of the protection through sorptivity testing. So an example of how you can actually do that is shown on that particular graph, where you can actually extract cores and actually just check for the rate of absorption of water. So I'm not going to go into too much detail on how you can actually calculate it. It's pretty self-explanatory. You can do that either by measuring the change in weight, which is the rate of water absorption, or by change in volume through sorptivity. And there is a number of both European and American standards actually enable you to do that. Now, in terms of the long-term performance, things are not as clear as one would definitely like. That is because there are very limited studies that have actually looked into that long-term performance of silanes. But typically, most of these will actually suggest that a life of between 10 to 15 years could be reasonable, but the exact performance will actually vary quite a lot. And that is because the materials also vary from one another. So you'll actually have that inherent variability, and they're very sensitive on the application conditions that we actually discussed earlier. Again, it is recommended that every few years some samples are taken from the actual structure in order to actually be able to verify the efficacy of the silane treatment. So in conclusion, silanes can actually be a very low cost and low maintenance application. They don't require a lot from one in order to actually be applied or actually any complicated designs. However, it needs to be recognized that it is actually, there's a lot of variability because of the proprietary materials. And one really needs to understand that when you actually apply it, it is providing this sort of invisible protection. One cannot actually see it by simply inspecting it. But equally, we need to actually understand and define what is the purpose that we want to actually achieve and how we can actually link it back into its long-term performance. Thank you very much. I do sincerely hope that you actually enjoyed today's presentation, and equally that you'll actually enjoy the rest of this webinar. Thank you very much.
Okay, so thank you, Christian, although not here present, for this interesting presentation.